Hello friends, welcome to the session on oscillators. In this session, we'll be discussing phase shift oscillator. In this session, we will see what we mean by RC oscillators, what is the need of RC oscillator. In this session, we will see the circuit diagram working and analysis of the phase shift oscillator. We will obtain the expression for frequency and condition for oscillations of the phase shift oscillator. Friends, as you know that you are viewing this session on my YouTube channel Learn with Prakash Kanade, and do subscribe to the channel to see many more videos on the subjects of electronics and computer science. So let us start the session with the question what we mean by RC oscillators. We know that any oscillator is an electronic circuit or device that is used to generate AC signal at the output. Oscillator do not have any input, and still it is possible that we can generate AC output. Already we have seen LC oscillators. In LC oscillators, we have seen Hartley oscillator and Colpitts oscillator. In these oscillators, the frequency of oscillation is being determined by the inductor and capacitor that are used in the feedback circuit. And this feedback circuit is a tuned circuit. Now we know that practically whenever we go for the values of inductor and capacitor, then we know that the values of inductor are in millihenry or microhenry, and the values of the capacitor that are commonly available, they are in microfarad or picofarad. It means that these values are very small, because milli it will stand for 10 to the minus 10 to the power minus 3, and micro it will stand for 10 to the power minus 6. Pico it will stand for 10 to the power minus 12. So the values of inductor and capacitor that are practically available are of very low values. And we know that L and C appears in the denominator in the expression for the frequency. And therefore, the frequency of Hartley oscillator or the frequency of Colpitts oscillator is very high. It is not possible to generate the low frequency oscillations by using LC oscillator, but many times we need an oscillator of which the frequency should be in the audio frequency range. And in such a case, we need to go for RC oscillators. RC oscillator are those oscillators where the feedback circuit consists of resistance capacitance network. And we know that the value of the resistance can be taken as high as possible, because the resistances are available in kilo ohms or in mega ohms also. There are two commonly used RC oscillators. The first one is being called as a phase shift oscillator, and the second one is being called as a Wien bridge oscillator. So we are going to discuss both of these oscillators. As far as this session is concerned, we will discuss phase shift oscillator in this session, and in another session, we will discuss Wien bridge oscillator. So these oscillators are used to generate low frequency oscillations. That is, the frequencies in the range of audio frequency range can be generated by using these oscillators. These oscillators are also sinusoidal oscillators. That is, at the output, we will be generating sine wave oscillations by making the use of phase shift oscillator and Wien bridge oscillator. So let us now go for the discussion of the phase shift oscillator. Phase shift oscillator, you can say, is an electronic circuit where the frequency of oscillation is being determined by the phase shift network, or the network that is being used in the feedback circuit, and this network is just nothing but a resistance capacitor network. This network is also called as ladder network. As shown in this diagram, suppose we have one capacitor and one resistance. Then there is a phase shift of 60 degrees for one particular input signal frequency. If we connect three such combinations of resistance and capacitor together, then this network is being called as a ladder network, and it will provide 60 plus 60 plus 60, that is 180 degree phase shift for one particular frequency signal. This oscillator will make the use of the three RC combination, and these RC combinations are being called as a ladder network. Phase shift oscillator will need an amplifier, because every oscillator will need an amplifier. So it will need an inverting amplifier and a ladder network. The output of the amplifier is to be coupled to the ladder network, and the output of the ladder network is coupled back to the input of the amplifier. So the ladder network that is being used in the phase shift oscillator is a feedback circuit. Phase shift oscillator is a low frequency oscillator, and it is possible that the frequency in the audio range or the frequencies up to several hertz can be generated by making the use of the phase shift oscillator. Audio frequency oscillator is a phase shift oscillator, and it can be used to generate the frequencies up to 10 kilohertz. By using transistor amplifier or by using operational amplifier, it is possible that we can construct the phase shift oscillator. High frequency oscillations cannot be generated by making the use of the phase shift oscillator because this is specifically designed to generate only low frequencies. This oscillator is very useful oscillator, and this oscillator is used in the musical instruments. So whenever you want to generate some audio tone, then in that case, you can make the use of this oscillator. This oscillator can also be used as a voice synthesis or GPS unit. This oscillator also generates the sinusoidal oscillation. So as far as the shape of the oscillations are concerned, at the output, we will get the sine wave at the output of this oscillator. Now let us go for the circuit diagram of the phase shift oscillator. As we know that for any oscillator, we require an amplifier along with a feedback circuit. So this is an amplifier circuit. This is a RC amplifier or CE amplifier. Observe that the transistor base is being connected to the base resistance, collector is being connected to the collector resistance, emitter is connected to the emitter resistance, emitter is also connected to one capacitor, and this capacitor will keep the AC potential at emitter equal to 0. The output of the amplifier is coupled back to a feedback circuit. So this is a feedback circuit which consists of 3 RC combinations, and the output of the feedback circuit is again coupled back to the input of the amplifier. The oscillations can be obtained at the output of the amplifier. So this circuit consists of a CE amplifier, that is a common emitter amplifier, along with a feedback circuit. The feedback circuit is a ladder network which will consist of 3 RC combinations. The output of the amplifier is coupled back to the input of the feedback circuit, and the output of the feedback circuit is coupled back to the input of the amplifier. Resistances RB, RC, RE, these are all biasing resistances, and they are adjusted to set the appropriate bias for the transistor. Coupling capacitors are used to couple only AC signal, and they are used to block the DC voltages. Now let us see how this oscillator works. Now, as we know that in case of any oscillator, always we require a starting voltage because oscillator do not have any AC input, and therefore the starting initial voltage is being provided by the noise signal that is being present at the input of the amplifier. This signal is being amplified by the amplifier, and as we know that amplifier is an inverting amplifier which will provide a phase shift of 180 degrees to all such input signal frequencies. Now we know that in the feedback circuit there are 3 RC combinations, and we know that one RC combination will provide a phase shift of 60 degrees. And when 3 such RC combinations are connected together, then all such 3 RC combinations will provide a phase shift of 180 degrees. And this phase shift will be provided only for one particular frequency, and that frequency is being determined by the components that are used in the feedback circuit. That is, the frequency of oscillation will not be decided by the amplifier, but it will be decided by the ladder network. And amplifier provides an 180 degree phase shift. The feedback circuit will provide an additional 180 degree phase shift. So there will be a total 360 degree phase shift, and therefore we can say that the positive feedback condition is being achieved. And when this Barkhausen condition A beta is equal to 1 is satisfied, that is when the product of the amplifier gain and the product of the feedback ratio is equal to 1, then we can say that the sustained oscillations are generated at the output of the amplifier. The frequency of oscillation is being decided by the RC combination or RC components that are used in the ladder network. So frequency of oscillation will not depend upon the C amplifier, but it will depend upon these RC components that are used in the ladder network. Now we can easily obtain the expression for the frequency of oscillation and condition for oscillation. Now suppose we will go for the analysis of the phase shift oscillator. And while doing the analysis, what we will do is that we will consider only the ladder network. Suppose there are 3 capacitors and 3 resistors connected here as shown in this diagram. Suppose V1 is the input to the ladder network, V2 is the output of the ladder network. The voltage at this point is V4, the voltage at this point is V3. The current flowing through the first capacitor is I1, the current flowing through the next capacitor is I2, the current flowing through the third capacitor is I3. And we will analyze the circuit from the reverse side. That is, we will start analyzing the circuit from the right hand side and then slowly we go to the left hand side. So as shown in this diagram, suppose we have a ladder network where V1 is the input voltage and V2 is the output voltage of the ladder network. Now from the figure, we can easily write this equation. V4, this voltage V4 is just nothing but V2, means the voltage across this resistance R plus the voltage across this capacitor C. The voltage across the capacitor C can be written as I3, means current multiplied by the reactance of the capacitor, that is I3 into 1 upon j omega C. But we know that this current I3, which is flowing through the capacitor C and resistance R, can be written as I3 is equal to V2 upon R. And therefore, we can rewrite the equation for V4 is equal to V2 plus V2 upon j omega CR. So this is just nothing but V2 in the bracket 1 plus 1 upon j omega CR. Now, so far we have obtained the expression for V2, we have obtained the expression for V4, and we have obtained the expression for I3. And now we will go for the expression for I2. Now we know that the current I2 is just nothing but I3 plus V4 upon R, because this current is being bifurcated. Some part of the I2 flows as I3 and the remaining part will flow through the resistance R. And the voltage across this resistance R is V4, and therefore I2 can be written as I3 plus V4 upon R. But I3 can be written as V2 upon R, and therefore we can write the equation for I2 as V2 upon R plus V4 can be written as V2 in the bracket 1 plus 1 upon j omega CR divided by R. And therefore, we can write equation for I2 as I2 is equal to V2 in the bracket 2 upon R plus 1 upon j omega CR square. Now we will go for the voltage V3. Now this is the voltage V3. The voltage is across this resistance, first resistance R. And this voltage is just nothing but this voltage V4 plus the voltage across the capacitor C. And therefore, we can write V3 is equal to V4 plus I2 into 1 upon j omega C, current multiplied by the reactance of the capacitor C. But V4 can be written as V2 in the bracket 1 plus 1 upon j omega CR. I2 can be written as V2 in the bracket 2 upon R plus 1 upon j omega CR square into 1 upon j omega C. Therefore, we can write the equation for V3 is equal to V2 in the bracket 1 plus 3 upon j omega CR minus 1 upon omega square C square R square. Now we will continue this analysis to obtain the expression for current I1. Now we have started from this side, right hand side, and slowly we are coming to the left hand side now. I1 is just nothing but I2 plus V3 upon R. So I1 is being bifurcated. Some part of the I1 flows as I2, the remaining part will flow through the resistance R, and therefore I1 can be written as I2 plus V3 upon R. Now we can substitute the value of I2 and V3, and therefore we can rewrite this equation I1 is equal to V2 in the bracket 2 upon R plus 1 upon j omega CR square plus V2 in the bracket 1 plus 3 upon j omega CR minus 1 upon omega square C square R square divided by R. So I1 can be written as V2 in the bracket 3 upon R plus 4 upon j omega CR square minus 1 upon omega square C square R cube. Now we can obtain the expression for the input voltage V1. Now V1 can be written as V3 plus I1 into 1 upon j omega C. Therefore, now we will substitute the value of V3 and I1. So we can rewrite the equation for V1 is V2 in the bracket 1 plus 3 upon j omega CR minus 1 upon omega square C square R square plus V2 in the bracket 3 upon R plus 4 upon j omega CR square minus 1 upon omega square C square R cube upon j omega C. So the same equation can be written as V1 is equal to V2 in the bracket 1 plus 6 upon j omega CR minus 5 upon omega square C square R square minus 1 upon j omega cube C cube R cube. Now we know that we do not want any imaginary term in this equation. And since we want the loop gain to be real, we want to equate the imaginary term to 0. And therefore, there are two terms which are containing j, and we will equate these two terms equal to 0. And therefore, 6 upon j omega cr minus 1 upon j omega cube c cube r cube is equal to 0. So this is just nothing but 6 minus 1 upon omega square r c square r square is equal to 0. That is just nothing but 6 is equal to 1 upon omega square c square r square. So this is just nothing but omega square is equal to 1 upon 6 r square c square. And therefore, we can get the expression for the frequency of oscillation as omega is equal to 1 upon under root 6 RC. Or we can write the same equation as the frequency f is equal to 1 upon 2 pi under root 6 RC. So this is the expression for the frequency of the phase shift oscillator. And one can easily observe that the frequency of the phase shift oscillator will depend upon the values of resistance R and capacitor C used in the ladder network. Now we can obtain the condition for oscillation. In the above expression, when we substitute the value of omega, then we can rewrite the equation for V1 as V1 is equal to V2 in the bracket 1 minus 5 into 6 R square C square divided by C square R square. Therefore, this is just nothing but V2 in the bracket 1 minus 30. And therefore, V1 is equal to minus 29 V2. So it means that the gain of the amplifier must be greater than 29 to produce the sustained oscillations, because we know that the Barkhausen condition has to be satisfied, that is A beta is equal to 1, and A beta is equal to 1 is possible only when the gain of the amplifier is greater than 29 to produce the sustained oscillations. So if this condition is satisfied, so whenever you go for the design of the amplifier for phase shift oscillator, then you need to keep the gain of the oscillator greater than 29. If this condition is satisfied, then the sustained oscillations will be produced at the output of the phase shift oscillator. So thank you, friends, for viewing the session. Hopefully you have understood what is the phase shift oscillator and how it works and how we can obtain the expression for frequency and condition for oscillations of the phase shift oscillator. Thank you all for viewing the session.